Today, we're breaking down a key required practical for your AQA GCSE Physics exam, the one all about acceleration.
Before you even think about trolleys and tracks, you've got to state the core principle. Well, this whole experiment, it's all designed to investigate one of the most famous equations in all of physics, Newton's second law of motion. You know it, force equals mass times acceleration. Just stating this by name right at the start sets a brilliant tone for your answer.
Stating the law is a great start for sure, but the question asks how you would investigate it. That means we need to get our hands dirty with the practical details. So how do we actually go about proving this in the lab?
You need to describe the setup and what you do so clearly that someone else could read it and do the exact same experiment. And a quick tip, a simple label diagram in your exam is a fantastic way to score marks here.
So what kit do you need? Well, you've got your trolley on a track, a piece of string that runs over a pulley, and some hanging masses which are going to provide the force. But the really crucial bit, the light gates connected to a data logger. These are amazing because they measure the time so accurately, which lets us calculate the acceleration with real precision.
If we want to see how force affects acceleration, we have to keep the total mass of the system the same. And the trick to doing that is to move the masses from the top of the trolley onto the hanger. See what that does? It increases the pulling force, but the total mass being accelerated, the trolley plus all the masses, stays exactly the same.
Right, so that's how we investigate force. Now, what about investigating mass? Well, here we change our approach. This time, we keep the pulling force on the string constant, so we don't change the hanging masses at all. Instead, we systematically add more mass directly onto the trolley. It's so important you explain that you're investigating each variable one at a time.
Talking about your control variables is absolutely essential for getting those higher marks. And the big one, the one you have to mention, is friction. We want the only force making the trolley accelerate to be from our hanging masses, right? So we have to deal with friction. And you can do that by tilting the track just a tiny bit so that when you give the trolley a gentle nudge, it rolls at a steady speed. That little detail shows you're really thinking like a physicist.
You've got to describe how you process that data and, crucially, what you expect to find.
Your first step is always to get those results into a clear, tidy table. Look at this one. The column headings have the name of the quantity and its unit. It seems like a small thing, but that kind of precision is exactly what examiners are looking for.
The next step is always to plot a graph. So for that first experiment, you'd plot acceleration on the y-axis against the force on the x-axis. And if you've done it right, your data should give you a beautiful straight line going right through the origin. That proves they are directly proportional.
And this slide just sums up those two key relationships perfectly. Your first graph, acceleration versus force, gives you that straight line, showing they're directly proportional. For your second investigation, when you plot acceleration against mass, you'd get that downward curve, which shows they are inversely proportional. As one goes up, the other comes down.
Okay, if you're serious about securing those top marks, you can't just stop at the results. You have to evaluate the experiment. That means thinking critically about what could have gone wrong and suggesting how you could make it better.
Now this table shows the perfect way to talk about errors. Don't just list a problem, like friction. No, you have to state the error, explain exactly how it affects your results, and then propose a specific practical improvement. For instance, using light gates instead of a stopwatch gets rid of human reaction time, which makes your data so much more accurate and reliable.
Oh, and a super quick point, don't forget to mention safety. It might seem obvious, but talking about things like catching the falling masses or stopping the trolley from flying off the end of the bench shows you've got a complete understanding of practical work. It's such an easy mark to pick up.
Okay then, how do we take everything we've covered and structure it into that perfect full marks answer?
At the end of the day, a top-level answer follows this exact structure. It's a clear, logical story. You state the theory, you detail the method, you describe your analysis, and you state a final conclusion that links everything right back to where you started. Follow this flow and you're golden.
And if you remember one thing, make it this. A good answer says what you did. A great answer explains why you did it. Linking your method, like moving the masses from the trolley to the hanger, back to the theory of F equals ma and the need to control variables, that's what shows real understanding.
So there you have it, all the tools you need for your exam. But you know, the physics doesn't just stop there. Newton's laws are fantastic for our everyday world. But what happens when things get really extreme, like speeds approaching the speed of light, or down at the tiny quantum level? That's when things get weird. But for now, that's a thought for another time. Good luck with your revision.